So I want to come back and have a second pass at the glass transition and look at it for some of the consequences of the glass transition, and also introduce a kind of a thermodynamically based classification for it. This is a plot showing strength modulus as a function of temperature, and it's imagined that at the low temperatures we have, polymer chains that are just sort of stuck in time. They're kinetically stopped. They are just not moving at all. Okay. But there may be some regions of free space in these chains remaining. When we heat it up, let's just pick this chain here. That chain can start to actually move. I'll draw it over here. And it can actually start to translate and move. Unless it's covalently cross-linked to the others, so that would make it a rubber. So as we got above the glass transition, and this is for the hypothetical case where there is no crystalline, okay, no crystals allowed in this plot. So if it's just a simple polymer that only could make glasses, and when you heat it up, it becomes a melt and it flows. Okay, unless there are crosslinks. If there are crosslinks, then we would have, even in the molten state here, well, above the glass transition state, in that case it wouldn't be flowing, it would just be executing nice little polymer wiggles. So we're going to put in some crosslinks here. If these crosslinks are present, this thing is a rubber. Okay. If they're not present, then it's a melt. Okay. But if it's a rubber, some residual strength will remain. Okay. So the modulus won't dive all the way to 0. It will still have some strength. Okay. Most polymers have a little bit of crystalline behavior to them. And in such a case as this, if we were to draw this polymer here, and let's allow it to make zigzag regions that are really some of the polymer can come in here and zigzag a little bit with that one, and we'll let that one exit over there. This one goes under there. Okay, so these little zigzag regions here, especially if they involve more chains than just one, these are crosslinks, and if you're cooling the sample down and you give it enough time to form those crystalline crosslinks, well, that behaves just like it was the covalently cross-linked rubber that we saw in the previous slide. So there's a little bit of modulus remains, and the more of these crystals you have, the more modulus you retain. But it all goes to hell once you get past the melting transition. So if we're heating this up, once we heat it up, we go from this, we get into the melting regime here, and the overall structure is still stabilized by these crystalline crosslinks here. until they disappear at the melting transition. Okay. And I just want to emphasize again, because I can't not do it, the melting transition has a term for freezing, either the freezing or melting transition, depending on if you're going down in temperature or up in temperature. The idea of a glass transition temperature, if it's creating a glass, that has to do with cessation of motion, just sudden cessation of motion. But I wish there was another term here called TL for libration. Libration means, liberal motion, so liberation of motion. So libration is, in this region between the TL/TG and the TF/TM. There's this, things are kind of moving, and in this case, in all cases shown here, there's some crystalline structure to hold the system together. But it will be much less brittle in that intermediate state. So this will be brittle. Okay, whereas here, this will be much more tough. Okay, and the reason is that even though these chains are held by the crosslinks in this zone, they can do a lot of wiggling. So this one chain here, we could draw, I'll draw this one here. Once it gets past its libration transition, once we go above TG or TL, we should draw it, so I'll try to draw the same shape, just that one chain. We can draw it as, and now it goes into that little crystal zone there. So here's the little crystal zone. But this backbone of that chain is all wiggly now. Okay, so it's all wiggly. And that means that if I hit this polymer with a hammer or something, I can excite all of those motions, those degrees of freedom for motion, and use them to dissipate the energy. Whereas if I try that down at a lower temperature below TG, I hit it with a hammer, it's just going to snap and break. We'll break some bonds and we'll break. Okay, so it's no surprise with all this motion going on up here in this regime above the TG but below TM, that we have these tough polymers. And so that's why you can take, your cell phone that's made of a tough polymer, and you can throw it around and it won't crack, it won't break, it'll absorb that energy. But it's no surprise that with all that extra motion that there should be a little extra volume. And so that's another way of looking at these systems, okay, is with the volume. And we really talk about the specific volume. This is really, what this really means is it's measured in cubic centimeters per gram. So that's a specific volume. So that means it's really, it's proportionate, well it is, it's 1 over the density. We use rho for density. Okay, so let's start. The purpose of this particular slide is to compare things that form crystals with things that form glasses, or things that do a little of both, depending. On the left is a typical fluid. Let's just say it's benzene. And up here, because benzene is easy for me to draw, we have all sorts of benzene molecules in different orientations because they're liquid. And they're spinning around and they're flipping upside down and doing all this stuff. So it's no surprise that comes with that extra volume. As they do all that, there's a little bit of volume in between them. And that volume in between the benzenes is called free volume. At the other extreme, if we go over here and look at a crystal, once we get below the melting / freezing temperature, we will form crystals, and now the benzenes will be all sort of packed somehow neatly. The actual crystal structure is not what I'm showing you, but it is known, and the main point is that they kind of are neatly organized assembly of stuff. And so that's more dense because I can get them all packed together and make it more dense. And so there is a sudden drop. If I'm cooling down, if I cool down here, I get to the freezing point, and assuming that there's no delay, sometimes there's a delay until the first crystal forms. But if I do this, slow enough, and I give the system time to respond, they'll just suddenly drop as these crystals form. It'd be a big sudden change. So let's contrast that with what happens over here. Just looking at the black curve, looking at this black curve, that's a system that didn't crystallize, okay, in this case. So what happened here is they took a system down, and they cooled it fast enough, or they didn't have enough seed crystals or something. There were no impurities in the system, because one of the things that favors the formation of crystals is impurities, because the molecule can go in there and it can just sit down on top of an impurity, and then another one can come on top, and then another one can come on top, and another one can come on top. So somehow making a system that's very clean and doesn't have any dust or any other flakes of metal or bits of hair or anything in it like that, it slows down the production of the crystals. So what happened in this case, if we follow this black line, as we cool, we blast right by the freezing / melting transition, and nothing happens until we get to a certain low temperature, and then everything just stops. But it's still disordered. It's still totally disordered. Okay, so it lacks the regular structure of a crystal. I have to draw these at different orientations. It lacks any kind of regular structure, just like it was a liquid, only the thing is it stopped moving. It's just stuck there in time. And this region in here is a supercooled liquid, okay? So that's what happens there. And these is kind of calling on a kind of a volume representation of this glass transition phenomenon. Well, all these things have to actually be measured. And there are experimental problems, and then there are real differences between glasses and crystals, okay? So if we try to measure some of the experimental challenges are things like heat transfer. So I can have a system, and I can take a chunk of polymer and I can put it in a fluid, and I can cool that fluid down. But the one thing that's difficult to do is to bury the thermometer right in the middle of the chunk of plastic. Usually we don't do that, okay? Because usually the chunk of plastic is, like a millimeter big or a couple millimeters big. So there can be kind of a lag between the reading of temperature that you make and the actual temperature inside the polymer. So that's one thing, and that applies to both TM, TF, and the TG, and I do like to call this the libration temperature, TL measurements, okay? So that applies to both. But there's more. But wait, there's more. As the salesmen always tell us, there's more. So let's imagine the case where we're starting up here at this temperature here, and we're going to cool down, okay? And we do go fast enough. Our cooling rate is T1. And they really mean the absolute magnitude of the cooling rate. So, maybe fast cooling rate, we can set these instruments that do this kind of thing. If it's a heat measuring instrument, not a volume measuring instrument, you can set that cooling rate pretty darn fast. Let's just say 50. Oops. How did that happen? How do I get rid of it? So set it really fast. 50 degrees centigrade per minute cooling. And T2 dot might be something much slower. This is a slower cooling rate. Let's say 5 degrees per minute. Okay? So we can control these things. And instruments are just sold to do that. Well, the slower cooling rate gives the system more time to sort of work its way into a better ordered structure. Okay? If I cool the system very fast along this T1 curve, I actually will record a glass transition that's too high. Okay? If I instead were to cool it at a slower cooling rate, I give it a chance, I give the system a chance to try to work its way into a more ordered situation. Okay? And if I really cool it slow enough, I may get it almost down here to have the same specific volume, which is really the inverse of density. Remember, this is the direction here is density going this way, and specific volume is going that way. So if I give it a lot of time, it's a thing called TG0 here, might be almost a really slow cooling rate. I might even get down to that. So your measured glass transition temperature depends on rate. Okay, in addition to the experimental problems that we could have either way. You could actually have a thing that's depending on rate. And there are a number of ways to think about this. One of them is to imagine that as you cool the sample down and you start telling the molecules move more slowly, move more slowly, move more slowly, what you'll find is that a given polymer chain, let's just say that it is polystyrene. Okay, let's suppose that we put up a polystyrene here. Here's a polystyrene. And one of the things that it can do is it can have, it has these little benzene rings sticking out of its side like that. So one of the kinds of motions that it has is a ring flips. It has these little ring flips. Like that little benzene ring can sort of spin around this little axis here. Here's another one. We'll spin it around that axis there. Okay, and that's spinning and spinning and spinning and spinning and spinning, and you slowly remove the temperature and it starts spinning more slowly. But look, this one here is in a different environment than that one there. Okay, so that's an important difference of glassing compared to freezing. If I talk about freezing, making a crystal of polymer, then all of these elements are either in a crystal, which is the same conformation everywhere, or they're in the amorphous phase, doing their amorphous thing, but there's only those two. But here, there's, if we're talking about glassing this thing, some of these benzene rings may want to stop before others. And there are other kinds of motion here that you can't go into. There's a kind of a crankshaft. If I get closer to the camera here, maybe like this. There's this kind of motion as we look at the bonds. It's a kind of crankshaft motion. And that'll be different at the ends of the chain than it might be in the middle of the chain. So there's all sorts of things that go on to keep this glass transition measurement kind of a complex thing. What if the polymer chain was at the surface and it's constrained to stay near the surface? Well, there's a whole large group up at Case Western Reserve University that got millions of dollars studying just that effect. We talk about a glass transition, and one of the reasons we're interested in it is because glassy polymers are brittle and hard. But maybe you can have that just at the surface, that brittly hard stuff, and then below the surface you have the sort of toughness that goes with being in the sort of above the glass transition, librating type of regime. Okay, this just reminds you again, I really wish we had words for this process that were different than we do, but we don't. Okay, so this just says the same thing I just went through, so I'll just leave that alone. There is, if you could measure at really slow cooling rates, this would be super slow cooling. Okay, and this kind of plot ignores things, the experimental problems. I should mention one other thing about glass transitions. We're talking about this sort of volume way, and that is an actual way that they can be measured. But in modern labs, they're often measured by things like solid-state NMR. And they can specifically go in and look at that benzene flipping around, that benzene ring on the polystyrene chain flipping around. They can specifically go look at a methyl group rotating around, or the other kinds of motions you have. And so you get slightly different numbers out of glass transitions according to what technique you use as well. So it's kind of a messy situation. Okay, so anyway, this is what a lot of materials do. This is the case here. This is sort of a general case. This is for a semi-crystalline polymer. A lot of them do this. And in many cases, we actually do the experiments on heating and not on cooling. It sort of depends on what you want. The heat flow experiments are done both heating and cooling, and you get slightly different answers in that too. But anyway, hopefully not. It still makes sense at the end. Okay, so here's a variety of materials. Reasonable question for an exam would be, I give you a plot like this and I say, what kind of material is it? Okay, the last thing I want to talk about here with glass retransitions is this business about thermodynamic order. And if you go to this slide, you know, underneath the slides, if you're in PowerPoint mode, the design mode, underneath them, there are notes. And I've been trying to print the notes along with the PDF versions of the slides too. This is probably one of the better written ones of those, okay? So I'm going to just do this fairly fast. I want you to remember one of the great equations that's worth remembering is this one. Changes in the Gibbs free energy are volume times changes in pressure minus entropy times changes in temperature. And G is a thermodynamic state function. And at some point in your mathematical career, you will, or already did, have the idea that mathematically speaking, we call that an exact function. And what that means is that these two terms that are leading here have a significance. For example, V, gee, keep bumping that. V is equal to partial derivative of G with respect to pressure, holding temperature and pressure constant. And S is equal to minus dG dt, holding, oops, this is silly, holding pressure constant. This one, I just got away, kind of run away here like that. There we go. All right, so there we go. Now it makes sense. Okay. So this is really a definition of volume, believe it or not, and this is a definition of entropy, believe it or not. And what we saw was that for crystallizing transitions, when I took that volume and plotted it as a function of temperature, it had this sort of discontinuity in it, like that, at the melting transition. Okay, so the thing that changed discontinuously was a volume or a first derivative of free energy. So these crystallizing transitions are called first order. It's first order transition because the first derivative of G, which is V, is discontinuous. Okay, discontinuity exists for the first order. If I look at glassing transitions, there was no discontinuity in the volume, it just changed slope. The discontinuity would be if I looked at dV dt versus t. And if I looked at dV dt versus t, now I have a discontinuity. Okay? But dV dt is, now I'm taking the second derivative. Okay, I'm taking a second derivative of free energy. So this is really taking oh my goodness. This is really taking, come on PowerPoint, be good, be good. I'm just going to have to write this elsewhere. Put it here. This means d of dg dp. It's a second derivative that is discontinuous. Okay, so these are second order. Second order transitions. That just says trans. But anyway, so summary is crystal transitions are first order transitions. glassing transitions are second-order transitions. And so this is a commonly used classification scheme for these two kinds of transitions. One of the last things I want to say about glasses is this business about whether a glass is a liquid or a solid. It's possible to think of them as a fluid, a liquid, but with an extremely high viscosity. The viscosity on going from a melt, a real molten liquid, to the glass can be something like 10 to the 17th, 10 to the 14th, 10 to the 15th times more viscosity. It's an enormous difference. Okay, and that shows here. And there are some. Here's I think this is actually for real glass as we put in windows or something. What you'll find here is that just look at the X scale. At the high temperature here, we have a viscosity in poises of maybe, what is that, 10, about 10 or 20 maybe, 10, 15. Let's just say 10 for the sake of convenience. And as we cool it down to a mere 400 degrees, the viscosity goes up by, it goes to 10 to the 15th or so. So, from here to here is 14, 10 to the 14th difference, so the 14 orders of magnitude. People will say orders of magnitude. Okay, so what you do, practically speaking, is when you're trying to get the glass to melt, you'll want to be sort of, in here working with the glass, and then you can actually draw it out and do things like a fluid. Here it's a little bit more resistant to flow. This is kind of just a softer, kind of a soft solid. And when you do a piece of work, which you can do in the glass shop, and if you want to come melt some glass, we'll be happy to help you do that in opal, for example. Or really, a specialty for this would be the mill. MSC's mill has a whole glass shop. It's really kind of nice. They make glass objects, artistic type things. But if you just want to melt a test tube or put something inside a vial and save it forever under vacuum, we can do that at opal. And what you'll see is that when you're done with doing something like that, you leave it at a high temperature. So if you take a piece of glasswork into the glass shop, Georgia Tech has an actual, the actual GT glass shop, which is over there in glass ship. Good. Glass shop. Okay. It's over there in the environmental science building. They have this glass shop. And if you take them a job and they put two pieces of glass together to make a reactor or something like that, or anything, they won't give it back to you until they've held it for a day or two at this kind of medium-high 400, 600 temperature range. And they anneal the glass and give it a time to work out any stresses that are built up from putting two pieces together. You may not get a total equilibrium. Okay. All right, now I want to talk a little bit about diffusion of polymers. And this is really cool because it leads us to subjects like polymer welding and stuff. And the first time I heard this, I thought it was nuts, but that was a long time ago. So in this video, they're going to show you about welding polymer membrane that's designed to keep stuff from leaking out of a landfill or something like that. And this is actually a company that's trying to sell you the training that's required to do that. But I think you can see it's fairly tedious work, but you can imagine that it's important. Let's see.
Welding geomembrane material, by either wedge or extrusion welding, is no job for an amateur. It's used for lining landfill sites, ponds, rainwater attenuation tanks, and gas barriers. Failure of such a liner in service just doesn't bear thinking about. The environmental and financial consequences would be huge, so training and certification for welding personnel is absolutely crucial. Lining technicians need to understand the increasingly sophisticated equipment in use and possess the knowledge to optimize equipment parameters like temperature, pressure, and speed for the task in hand. Coping with different thicknesses of material, alternative equipment, and ever-changing ambient conditions of site work all need to be accommodated safely and competently. A lining technician's knowledge must include the interpretation of weld quality by visual inspection as well as destructive testing methods, using these things: site tensometers. For more than a decade, the certification of lining technicians has been mandatory under Environmental Agency rules. TWI's structured courses provide guidance and best practice on precisely how to carry out geomembrane welding successfully, safely, and efficiently by wedge and extrusion welding. The courses culminate in an examination which leads to...
Well, I think that's enough to give the idea, and I'm skeptical that this can be done without any leaks, but maybe the rate of leaking can be slowed enough that it doesn't matter. So the idea, of course, is that you have some toxic thing and you're going to put it in this landfill, and it should not go into the water table below. We're very lucky where I am in Baton Rouge because our water actually started in northern Georgia. They say maybe 10,000 years ago, and it's just now reached us. So it's very pure water. We have extremely pure water in Baton Rouge. There's hardly any point trying to purify it. It's different for those people in New Orleans. I do not drink the water there. And it's different for you all in Atlanta. I don't even know that what comes out of a tap in Atlanta should be called water. It's pretty awful. But in any case, the question is, how do you weld polymers? And the way it works, is, I think I'll make this a little bigger. Imagine my fingers being polymer chains, and I get up beyond the glass transition temperature and beyond the crystal melting transition temperature, and so now I have motion. I have real translational motion of these things, and one can come around and loop like that and make an entanglement. And entanglements, once I cool that down, maybe even some crystals will form in there. I guess we'll have crystals like that. But entanglements and crystals will hold that system together. And the process, this whole idea of polymers moving and then therefore being weldable, also pertains to creation of milk bottles, plastic milk jugs that we drink from, Coke. Everything kind of rests on this diffusion and also the viscosity of the polymers, and those are related things. What I want to do now is try to show another YouTube.
C-SWIP certification, a recognized standard of quality, underpinned by the European standard BS.
And start. Really? Oh, I did. I ran it to the end. I want to talk about the polymer reptation, and this is shown by a simulation. Nothing is moving yet. The little dots that you see are meant to be polymer chains going into or out of the plane of the paper. So we have this mixture of polymers. Some are coming out of the plane of the paper, and those you see as dots, paper, screen, coming out of the screen, and they see those as dots, and you see the other ones are going to be diffusing. And they diffuse in a kind of snake-like motion. And snakes are reptiles, so this is called polymer reptation. Okay, and so you'll see what happens. Because the chains try to get around the little green things, and they sometimes can eventually. But you see it's a fairly slow process. A different way to imagine this would be to cook some spaghetti, which actually would be good about now. Let's see if I get this to be larger again. Really? I don't care about my calendar. I just want to be large enough that you can see me. Okay. Going to be that way, are we? All right. So be it. Imagine a thought experiment. This is what Einstein got famous for doing, is to imagine things. And imagine that you cook some noodles. Spaghetti noodles would be fine. Ramen would be fine. And you drain them, drain most of the fluids out of them, but you don't let them really go to dry yet. You just drain them. And you take a big spoonful and you put it on a plate. And you take another spoonful and put it right next to it on the same plate. Well, they'll sit there forever. They will not merge into each other because they're macroscopically large objects. But if it was molecules, we have random Brownian motion. What drives that reptation that you just saw is random Brownian motion on the whole chain. And as a result of that, it's like the little strands of spaghetti from one wad of spaghetti will mix with strands from the other wad of spaghetti, and you will blend them. On the molecular scale, that's what happens, and that's what this polymer welding is all about. And so you saw that as they were making that geomembrane, they were heating it and melting it, getting it above, of course, the glass transition temperature. It was always above the glass transition temperature. And they got it above the crystal melting transition temperature too, long enough that the chains could interpenetrate like that, and cure the seam, and go and seal that seam up, and then they let it cool back down. The crystals reform. The chain motion, basically stops. And you now have, as though you had removed the seam. And then the claim is that you can do this perfectly. Well, of course, I'm skeptical about that. But anyway, probably it beats not sealing off these landfills. I thought another thing that I wanted to show you was a little bit about the Spunbond, making of Spunbond polypropylene for masks. And I think these two lead us to videos on that. Let's see what happens. This is good.
Non-woven web formation is accomplished using one of three general methods. 1. Dry laid. In this process, raw fibers are mechanically aligned and then laid out, or they are dispersed into an air stream and collected on a belt to create a sheet. When air is used, the process is referred to as air laid. 2. Wet laid. A suspension of raw fibers in water is deposited on a porous belt to create a sheet. 3. Spun melt. In this process, polymer is melted and extruded to create filaments, which are then directly laid onto a belt to create a sheet. The two most common variants of this method are spun bonding and melt blowing.
So the spun bonding and melt blowing techniques are what are used to make the polypropylene for the masks that we need. I looked on YouTube a fairly long time to find an American factory that showed this. I did not. So this is a modern looking factory. Let's see, I'm going to pause this if I can for a minute and try to explain what's going on. I think what's going on. This sort of salmon colored thing that you see where my cursor is pointing now, I think I have, no, I don't get that. That is a belt, okay? And the white stuff coming off it is the melt blown, spun bond, whatever, polypropylene. And we want that melt blown spun bond thing because the other two processes that you looked at in the previous video probably leave a number of fibers that, you know, could come off when you breathe, and you don't want to be breathing the fibers. So you want the fibers to be all, you know, into this sort of non-woven material. You could imagine the stuff that lines a jacket or a parka or something like that. But you want it sort of held together. So it's held together by these like welding on a tiny scale of the fibers. The system is heated up enough that the fibers go and touch each other and reptate just enough to hold all the fibers together reasonably well. And that will survive breathing okay. Anyway, so let's continue the video. And I think this is live. You can see the rate at which they're able to produce this stuff in some countries anyway. Countries that didn't give up on manufacturing because they wanted quick profits in the stock market. And then it has to be rolled up onto these big things and shipped off to manufacturers. Here it comes off the end. All the videos I could find like to show you the end of it first. The really interesting part happens at the beginning, which is at the end of the video. Oh, this is great. See, here's that salmon colored belt, and what they're going to do is melt a bunch of polypropylene and spin it into tiny little fibers and then blow air onto it as it hits that belt. And that's what makes the white product that you're seeing. I don't know what's going on here. Maybe they've divided the streams into several streams. I don't know. Maybe they're recycling. Anything they cut off, they will recycle and put back in. If you have to trim some of the material, they will capture that and melt it again. You could do that multiple times without a problem. Okay, this is a slowly turning thing. It makes me think that's an engine driving a take-up reel, or maybe the impeller that melts the beads. Okay, all right. You get the idea of a pretty large, modern-looking factory. And I don't think you could set something like this up overnight, but it's incomprehensible to me that it can't be set up 6 or 7 months into a pandemic, that multiple ones of them couldn't be set up in that kind of time frame if you put a lot of money into it. I think you could do that. And if you go look around, here's again the salmon colored belt, and you see the rate at which that stuff is blown on there. And then it's just a take up after that. They just take it up and process it. So that's a little bit about processing. And material science is very much a processing-oriented thing, as we saw back when we were looking at nucleation and growth versus spinodal decomposition. I'll let you watch some of these on your own. But again, if you can imagine how a milk carton is made, I guess we'll watch a little bit of this one. I think it's okay. Not too long. Always the dumb music. I don't know why.
The main sections of a reciprocal screw extrusion blow molding machine are the hopper, an externally heated feed barrel, a reciprocal screw which has a feed zone, compression zone, and metering zone, and the head and die assembly. Resin, usually in the form of plastic pellets, is fed to the feed barrel from the hopper. This hopper may be filled manually or vacuum fed automatically. As the resin enters the feed barrel, it is driven forward by the rotation of the screw. The resin begins to melt as it is moved forward due to both the frictional shearing forces generated by the rotation of the screw and the heat from external heating bands attached to the feed barrel. The melted resin builds up in pressure as it is compressed and confined at the end of the feed barrel. To control this pressure buildup, the rotating screw is retracted. Once the proper amount of melted resin is available, the screw is hydraulically forced forward. This rapidly forces the homogeneous melt through the extruder's head and die assembly to form a parison.
So that was the formation of the what's called the parison, spelled like that. And then what you do is you take that sort of oozing thin cylinder that's coming out of the hot die, and you push it into a container and seal it up, okay? And while it's hot, the polymer has to flow together, again by this process. The polymer molecules have to interdigitate by this process of reptation, okay? And at that point, then you can blow air in and shape it. So I think that will be shown here.
Blow molding processes are the most popular methods used to produce hollow products out of thermoplastic materials. Blow molding evolved from the ancient art of glass blowing. Today, it is a leading plastic manufacturing process because of the wide range of plastic resins that can be blow molded and the many possible methods of blow molding. Blow molded parts range in size from the very small to extremely large parts.
It's a gas tank, I think.
Bottles and containers are the most common blow-molded products, but other items such as highway barrels, automotive components, double-walled cases, toys, medical items, and structural panels are produced. Blow-molded products are formed from thermoplastic resins such as high-density polyethylene, medium and low-density polyethylene, polyethylene terephthalate, polypropylene, polyvinyl chloride, thermoplastic elastomers, polystyrene, polycarbonate, fluoropolymers, polyamide, and many other materials. Most thermoplastic blow-molded products are produced via extrusion blow molding using high-density polyethylene or HDPE, but there are many additional blow molding processes which include injection blow molding, biaxial stretch blow molding, and co-extrusion blow molding. These blow molding processes all use elements of either extrusion or injection molding, or a combination of the two. In addition, these blow molding processes all share 4 common stages: plasticizing or melting the resin, Parison production, when referring to most blow molding operations, or preform production, when referring to biaxial stretch blow molding. Parison or preform inflation and cooling in the blow mold, and ejection from the blow mold. A fifth stage is necessary in extrusion blow molding for trimming and finishing the product. For the most part, blow molding processes all use the same blowing technique, whether it be through a blow pin, a needle, a stuffer, or core rod. It is in the production of the parison, or the preform, where these processes differ. The process of extrusion blow molding involves applying.
Oh, I think that's enough now. You can watch this as you wish later if you want to see more. You get the general idea. But again, it comes down to the processes we've studied about. You have to heat it up until any crystals are gone so that it flows. And then you have to blow it into the shape and then shape it. You have to overcome a lot of viscosity to do that. It's a big deal to be able to do that because overcoming viscosity involves temperature. Temperature involves heat. Okay. Nevertheless, the production of these plastic bottles has just overtaken everything else, any other ways that we used to have to do it. And we really are making so much of this stuff now that we really even have a problem with what to do about it. The other thing I like to call attention to is that you will see on the GT campus and in a lot of research labs, emphasis on 3D processing. Okay, so you additive manufacture, 3D printing of objects. Well, there is no way to 3D print these objects as fast as you saw there. Okay, so this is a thing for specialty objects. For example, maybe you made by one of these processes, either blow molding or some other injection type process. Maybe you made a door handle, okay, and after 20 years, that door handle was cracked. Well, in the bad old days, which is like 10 years ago, you had to have a warehouse full of the old door handles. So when they made 100,000 cars, they made 110,000 door handles times 4 if it's a 4-door car. And they have some spare door handles hanging around in a warehouse, and you have to keep them. You have to have them in a database and everything else. And then you have to hope somebody eventually buys them. You never really know. Now, because of additive manufacture, all you really have to keep is the blueprint, SolidWorks drawing, if you do SolidWorks or AutoCAD or whatever you use. You have to keep that drawing, and you can 3D print yourself the right shaped door handle for that car, and solves a warehouse type problem. But in terms of making hundreds and thousands of objects, I think it'll be a while before any kind of additive manufacturing is really competitive with that speed. Let's see if it'll let me out of here.
And heat and pressure to thermoplastic resin to produce what?
Stop. Okay, let's close that. I'll let you watch that other one on your own. Oops, what was this one? Polymer welding and reptation. We talked about. Last thing I want to talk about here very briefly is other ways that we can get structure out of polymers. As we said multiple times, they're this sort of wiggly, random, coil, random, messy-looking spaghetti things, and they don't really seem like they would have structure. But we've seen it happen. We saw that they do form crystals. We saw that they can undergo spinodal decomposition to make a sort of spongy structure. There is a couple other things that we can do. Certain polymers will make liquid crystals, okay? And liquid crystal polymers tend to be long molecules. They tend to be straight. And so unlike most polymers, there are certain rod-like polymers, and I think we mentioned this way back many slides ago, that just sort of stay straight as a result of their basic chemistry. And these things can make liquid crystals, and in a liquid crystal, basically, the molecules are aligned, sort of like, they're all sort of aligned this way. Okay. And that gives us some high strength opportunities. In this particular liquid crystal, there's a plane of molecules with that orientation, and then sitting on top of it, put it in a different color, there would be a plane of molecules with this orientation, right where I'm drawing in this sort of gray region here. Okay, and that is what is called a cholesteric liquid crystal. Okay, and so that's what's happening in this sort of gray region, is that these, and then there's even other layers beyond that. There's other layers with different orientations. Here's one put in a green layer. These are all the same molecule. The color is artificial just to indicate that blue is on the bottom, then red, then green, or something like that. And so these are systems that have decided to molecules align pretty much straight, but then they do a kind of a sort of weird twisting thing, and this is a result of their chemistry. And that's one kind of liquid crystal. There are others. Polymer liquid crystals are useful for making high-strength fibers, but they're not very useful for making displays, for the reason that sort of hounds polymer science always is they're just slow. Because they're such large molecules, they're too slow. So liquid crystal displays are made of other molecules, same basic rod-like shape, but much smaller, and so they're fast. This is a phase diagram for a particular rod-like polymer, and two particular rod-like polymers, actually. And what I want to just emphasize is that if you do one of these temperature, this is like a temperature composition phase diagram like we were studying a few slides back. If I do some sort of cooling transition, these tend to make gels. It's by spinodal decomposition. These rod-like polymers tend to be really good at spinodal decomposition because they tend to have a narrow metastability gap. The phase diagram, if I was to try to draw the spinodal in here, it probably lays pretty flat across there like that. Okay, that's to oversimplify a lot. Here is how we make ultra-high strength fibers like Michelin puts into their tires, Aramid tires, and Air Force builds composite fibers for aircraft out of. What you basically do is you take a liquid crystal up in here, you have your polymer in a liquid crystal, in a solution usually, and you force it through this die. This is called a spinneret. It's kind of hard to read there, but the word is spinneret. And you can think of this as a shower head like you have when you're taking a shower. So you take this liquid crystal and you push it with pressure through this shower, and you dump it into a coagulation bath, and you try to trap all the molecules, all the rod-like molecules, laid out straight like that if you can. And then you wash out the solvent. There's usually some horrible solvent. Liquid crystals usually don't dissolve in nice solvent. So you try to wash away the solvent to recycle it, take that fiber up, and then you make a composite material out of that. Again, the importance of processing, okay? I don't want to talk about that. Building with blocks. So we talked about block copolymers, and a really common one for sort of fundamental study is this. Here's a styrene isoprene die block with n units of polystyrene and n units of isoprene. And this can be made in huge factories by the ton, and they can make it with enormous precision. N doesn't have to be the same for the styrene block as it does for the isoprene block. They can control all these things at several tons production, no problem. Here's one that's styrene isoprene styrene block. Okay, so the styrene is the hard polymer in this because it has a relatively high glass transition temperature, so that means that we're usually operating below the glass transition temperature, and it's kind of a brittle material. And then the isoprene has a much lower glass transition temperature, and we're usually operating above that. So I have the thing with sort of a stiff component and soft component in the same polymer. Well, what you find is that these materials, the parts of the chains, don't really want to mix, okay? And so they will form domains. This is for like the terpolymer, polystyrene, polyisoprene, polystyrene. And since I can make all the blue ones the same length, and really they should kind of go through here and connect through. So the blue ones will be in some sort of zone, and there'll be a length of the green ones, and then that'll be connected through somewhere over here to another polystyrene blue block. And it makes these microdomains, and there's a lot of effort in trying to make that a uniform shape, and I don't really follow the latest on that, but here's one that's looking a little better, and this is an electron microscope trick to get the visualization of those domains, and you can see that there is some sort of structure there. What everybody really wants to do is have that same structure on a much larger scale. There's no scale bar on this, unfortunately, but I assure you that's a pretty small scale. And you'd really like to have that on a much larger scale. And what would you do if you could do that? Well, you might try to make an optical device. So maybe you will take in the white phase, let's say the white phase, will bury little gold particles or something that absorbs light. And then they'll be nicely and uniformly spaced, okay, because we're only going to let them be in the white block. Okay, so that would give us a nice uniform spacing, which we could use for making a diffraction grating or some other optical element. That's previous structure is called the lamellar type structure. There are much more complicated structures. There's a huge amount of work went into figuring out the various structures, and this one is a little bit hard to follow, but trust me, there's a sort of a interpenetrating two-phase structure inside of that people worked hard to determine. And there were a lot of arguments about that too. Well, we've reached the end. 172 slides in this slide deck. You have gotten more polymers than most people do in MSc classes, but it is really an important class of materials. And we said we were going to start off by trying to understand the scale of polymer production. It really is, tons per factory per day. And there's lots of factories, and you saw even making the spun mass that kind of comes whipping off that assembly line pretty fast. We wanted to talk about the difference between a condensation and addition type polymerizations. I think we did that. These are often now called chain growth and step growth. We tried to understand molecular weight distributions. I bet you know more about Mn, Mw, and even Mz now. I bet you know things like GPC a little bit, that at least exists. Maybe you're slightly familiar with some of the biopolymers. There's no way to know them all. Nature makes the most amazing molecules. I was looking at one today, heparin sulfate, that may be able to inhibit viral replication. So we got our fingers crossed on that biopolymer. The difference between absolute and calibrated molecular weight determinations. We get absolute molecular weights from things like osmometer, which relies on thermodynamics, or spectroscopy, which just relies on the ability to count spectral peaks. Maybe a little bit about phase relationships, maybe for the first time for many of you to see a liquid-liquid phase relationships, not just the usual solid liquid gas stuff. Tacticity controls the stereochemistry or the orientation of the substituents on the chain, and this controls whether or not it can crystallize. It's one of the things that does. We talked about two measures of size. One was called R G, or maybe we called it the center of mass radius, so the average distance of the polymer subunits from the center of mass. And we also talked about a thing called the hydrodynamic radius, so we talked about that a little bit. We talked about fractal dimensions, df. Okay, for solid objects it was 3. For polymers, much closer to 2. We didn't really talk too much about soft particles. We did talk a little bit about latex and how we could choose to do the polymerization of the monomers in a suspension. You know, we could oil and water, oil being the monomer. They're oily. They're not really oil like you put in your car, but they're organic liquids that are sort of oily. We call them oil. So anyway, the oil type part and the water don't really mix, but if you stir them like crazy, you know, they stay in these little blobs, and then you can polymerize those blobs, and you wind up with a bunch of little beads that disperse in water, so you can do a water cleanup instead of the usual volatile organics and cancer-causing solvents. But why we did this was really, I mean, I'm glad that you got this polymer knowledge, but what I really wanted to do was to encounter a bunch of other stuff in this polymer world that we can use to understand other materials. Most of the engineering and most of the physics disciplines and physical chemistry, anything that's sort of physical, there is an awful lot to be gained by look for the things that are common. So what do we learn that applies across the board to a bunch of materials? We're really big on that in MSc. We chose the polymers as a kind of vehicle to understand some of these basic things and not really understand them deeply because we got a whole 2/3 of a semester ahead of us. We used polymers to introduce mutual and self-diffusion. Okay, the self-diffusion was just particles executing kind of a random walk type motion. Okay, there was no real change in the overall concentration. Other particles are there and they stay at whatever concentration. They're all moving, but the overall concentration doesn't change. The mutual, so that was our self. The mutual diffusion coefficient was, let's put a bunch of them here in this box. And we'll imagine a little artificial gate. And we'll say, we'll remove the gate and say everybody go. And so now the concentration is high on the left to begin with, but it's going to spread out. That's the mutual diffusion, and we'll talk about that. Both matter. We used polymers to introduce Arrhenius behavior, viscoelasticity, because polymers are both. Think about those jello cubes bouncing around. I mean, you know, that was definitely an elastic type motion when they bounced, but it didn't last very long. It dampened out pretty quick. We learned composition phase diagrams, cooling and heating plots, heat input versus time, or heat output versus time. We'll see that again. Supercooling, we may see that again. We talked about glasses kind of ad nauseum. They're really basically kinetically trapped liquids. So they have the structure of a liquid, only nothing is moving. Okay. We talked about the importance of processing. We can choose a path that puts us in the metastable region, then we get nucleation and growth. we can choose another path that puts us right through the metastable region very fast and get immediately spinodal decomposition. The nucleation and growth gave us this kind of structure, little droplets of stuff immersed in other stuff. And the spinodal decomposition gave us worms. Well, not hopefully stomach worms or anything like that, not like your dog has worms, but it gave us these sort of, you know, bicontinuous structures. So this was the nucleation and growth, and that was the spinodal decomposition. And because they're polymers, and because polymers are such slow molecules, you can stop these things. You can kinetically stop them. And they're stuck like that basically forever. And I could use the one at the left for maybe delivering some cargo that, you know, exists in these things like perfume or a drug or something. And I can use the one on the right maybe for a filter. You know, molecules that are smaller than these openings go through. Molecules that are not smaller than these openings don't go through. And actually, real filters are made in this way. We talked about the different radii. We talked about how we would measure dynamic and light scattering and intro. We may be able to talk a little bit more about scattering for other materials. Again, the importance of processing. We talked a little bit about light, how there's this pointing vector, should be a vector, should underline that. We talked about light having a vertical and a horizontal component. The vertical would be the electric field, the horizontal would be the magnetic field. When we pass the light through a crystal, just looking at the electronic field, it splits into two. One is called ordinary, the other is called extraordinary. And this leads to colors and evidence of, this is how we understand the formation of crystals in a lot of materials. And much to the dismay of some of you, we even did a tiny bit of electron pushing, and we didn't do too much electron pushing of organic chemistry reaction mechanisms, but we did a little bit, and hopefully enough that you will recognize it and not be too intimidated by it in the future. That's kind of one of the reasons for going to college or university, is that you get exposed to this stuff, and maybe you really don't 100% understand it, but you understand that somebody understands it. And you don't have to be totally afraid, and you don't have to make your decisions based on random choices. So that is really all I wanted to say about polymers, and it took a while, but I hope it was worth it, and we'll see if we can reuse and recycle some of that information as we go into other parts of the course.